Awesome, thank you. So I'll start off with a couple slides, and then Jeff's got a couple slides at the end, and then we'll break off for questions. So this is digital engineering transformation, the challenges and vision. So this, like Julia said, is the second talk. The first talk focused on kind of where we came from a digital engineering standpoint, how we've transformed in the past from a paper approach to a more digital approach. And there's a lot of questions on, well, what does that leave us moving forward? What is the vision moving forward? So this slide is where we left off on the last presentation. So we'll just kind of review this real quick. My analogy here was the digital transformation is going to be similar to the music industry, where you had your CDs and then we went digital, and there was some issues, during that transformation with standardization, but eventually we end up with some good solutions that we can all agree is better than having a stack of CDs in your car. So that's the analogy here. We're trying to move from a document-centric approach to a model-centric approach, where we can use computers' capabilities like tagging and all sorts of other features that we're all familiar with at this point, to help us develop and accelerate faster. So MBSE is model-based systems engineering, and it consists of three major pillars: the methodology, the language, and the tool. So the methodology is kind of the process in which you go through to create your models, the package structure, and just the way that everybody is aligned, that they're gonna all model the same way. The language is, in this case, SysML or UML, and the tool, the architecture tool, is what we're talking about here, is probably going to be like Cameo or MagicDraw or Rhapsody. So moving on, achieving the digital thread. So the reason that we're trying to thread is for the 9 items that you're seeing on the right side of the screen. One of the big ones is removing the ability to lock in a vendor, so that like the government can will be able to find you create like a more modular sort of system, where you can build just an entire system and then have your propulsion system be bid out to different contractors. And this digital thread that you're seeing on the left side of the screen, one of them would be the architecture tool or the software, and then you would connect to other software suites, such as like requirement software suites like Doors Next Gen or Doors or JAMA. And you have simulation softwares such as MATLAB. And the idea here is that you would be able to send data back and forth in a quick, efficient manner and automatically between tool sets, so that your mechanical tool set could talk to your requirements tool set, and be able to just work and play together. And I'm sure you can see that that's a lot of setup between the API calls, between the tools, and you have a lot of churn between different tools trying to be as compatible as they can, versus some tools are trying to just be compatible with other tool suites that company has created. So we'll kind of go through the digital engineering environment and the tool suites and some of the challenges that we have currently, and what is going to go on in the future. So right now we'll talk about the internal and external struggles that we've got, and we'll break it down into 3 major groups: the model to model interdependencies, where we don't have a quite standard approach for putting models together. A way that you would be compatible is if you all agreed upon the same methodology, but the devil's in the details there. You really have to agree to even pass the methodology there's still a lot of gray space. So that is an issue, because essentially you would have a systems model, and then you'd have a subsystem model, and then even a component model, or a system of systems model, and they all have to work and play together, and using the same methodology is critical. Additionally, so now we're kind of zooming out a little bit. Number 2 is the tool-to-tool compatibility, which is your architecture tool, which we talked about earlier, is Cameo or MagicDraw or Rhapsody, are your 3 main tool suites that are used for the architecture tool. But then you also have requirements tools and simulation tools, and there's lots of other domains of tools. You'll have one for mechanical engineering, electrical engineering, software engineering. So connecting these tools creates it's not super easy to do, and it's not automatic. So you have several different options that we'll talk about to kind of develop that compatibility. And then if you zoom out a little bit further, we have the DEE, which is Digital Engineering Environment, to DEE. So Raytheon would have their own environment, and then the Navy or the Air Force would have their own environment. And so sometimes you would have to, or your supplier, for example, Raytheon supplier would have their own environment. So we would need to be able to communicate parts of our model to the supplier or to the Air Force. So it's being compatible between DEEs. So we got 3 different levels of complexity here and compatibility. So we'll start with number 1, back to the zoomed in view, model to model. So we're moving from chaos to ordered chaos. So we have a bunch of variants right now. The industry, we've got the company. So some companies have dedicated significantly more resources to this effort. So we'll have like some government contracts which are pushing this model-based systems engineering really hard and make it a requirement to create a system. And so now as a contractor, we have to decide, are we going to make our subsystem suppliers also have models? Are we going to impose those same requirements onto them? And are we really going to change who we're purchasing this part from or assembly from based on if they can model? And so, you know, some of these smaller companies that create assemblies may not be as focused or dedicated to this effort. And so it's an interesting mix of expertise between companies. Additionally, we have the project within the company. We just don't have a lot of people that know how to model very detailed or in a good way. So we have pockets within a company that you'll see work that's done well, but then you'll also have other pockets within that company that are not on the right track. So we're trying to, we need to, you know, train the workforce, which is what I do. And then we also have different complexity and scope of the model itself. Some models are pretty simple, some are really, really complex, and project use like 40 other models. So they have to be flexible in size as well as which domain it's talking about. You could have a model that's just focused on, you know, fixing this one aspect of simulation, or it's, you know, there's a focus to the model as opposed to just model everything. And then finally, we have delivery of the product. We're also talking about the DEE to DEE. Like it changes what's written in the contract of, are we just providing them a file, or are we providing them a file and an environment, or are we supposed to make our file work on their environment? So there's a lot of, you know, differences and not much standardization. So, and my example that I have here that I've run into several times is that you're seeing on the right side of the screen, and I've got my little pendulum where it goes back and forth, is for 6 months we'll go the library book method, and then 6 months we'll go the shopping cart method. And the library book method is basically we have a library full of all of our blocks and elements that we've created for, I don't know, an unclassified Raytheon project. And then we can use this library and check out our USB block that has all the details about USB and use it, reuse it. It's a great method. But then Raytheon doesn't want to share that with anybody else. So there comes a problem. And then, Raytheon doesn't want to send it to the classified space. So there comes another problem. So it's a clean and neat method, the library book method, but companies are trying to keep their stuff proprietary, which is pushing away from this reusability sort of situation. So then they come out with the shopping cart method, which is basically you drive around your store and you pick up an apple, which in this case would be your element or your block or whatever. And instead of, you don't return the apple to the store, you just use it, you consume it. So it's more of a copy paste sort of situation where you've got apples everywhere in your model. And it's great for being severable. So the model itself can stand alone. But it becomes messy when you have apples everywhere. So that's kind of just one quick example of where there's a bunch of gray area, and it needs some standardization. So moving on to tools. So this is software suites to software suites. And this is the development over time. So the left would be where we started, the middle is where we are, and then the right is where we're going potentially. So we're trying to build out the threads, which are the lines between the blue dots, and the blue dots are the software tools. So I'll try to explain kind of what we're doing and why we're doing it. So the problem is the tools are not easily compatible between this architecture tool and the test management tool. I'm looking at the very bottom left and that dotted red line. So now we have options. Do we purchase another tool? Or do we create a plugin from scratch? Do we pay a third party to create that plugin? Or do we replace the architecture tool with something else? So then we decided to purchase another tool, which you're seeing the model manager tool in the middle. And so now we have to kind of recreate our architecture of our tool-to-tool compatibility, because now we have a different, the architecture tool is still the middle of the pie, which will create a problem with configuration management, which is what you're seeing with the problem there. Configuration management and version control is more difficult. A hub and spoke architecture would be more preferred. So then we go to the right side and we've changed our architecture, and then we have to recreate these plugins, because now we're creating plugins between the model manager and the requirements instead of the architecture and the requirements. So it kind of turns into this circular problem of, okay, these API calls are difficult to make. What's the best architecture moving forward? So all that to say is, with time, a good architecture will be created. I think that, and also each of these blue circles that you see, there's multiple different alternatives for potential architecture tools and requirements tools and model manager tools. So it's not just like two-dimensional like you're seeing here. It's more like it gets to be complicated. All right, so now DEE to DEE, so digital engineering environment compatibility. So at this point, the government entities have created virtual machines to host these environments. Many contracting companies have also created DEEs to work and push their tool sets. This results in integration challenges as we try to give our models to whoever we're providing them to. And even if you have the same sort of digital engineering environment set up, sometimes there's still issues porting things over. One of the IRADs that I am working on right now is actually kind of like a Google Drive between these DE environments. It's kind of interesting. So what I was talking about before this talk actually was how there's just a bunch of startup companies that are either creating API calls between different tools. So the tool suites between the different blue circles there, but then there's also startups that are working on connecting between DEE to DEE. So there's definitely space to grow, and there's definitely a flail going on right now, but we'll figure it out. So what's going on in the future? So more libraries will become open source. Right now, like I said, everybody's trying to keep their special library close to their chest and not let anybody else see it. Eventually, there will be more of an open source sort of situation. Risk management improvements. Yeah, there's systems engineering risk is one of them that we focus on, and the architecture tools need to improve on that, and they will. They are. A reliable method to deal with sharing libraries in different environments will be standardized. So there's a lot of issues between moving things between unclassified and classified spaces, and between contractor 1 to contractor 2. So there just needs to be a better way to do that. And then there's a culture shift. Design reviews and milestone decisions will be presented from the model versus PowerPoint. I think we're about there right now. I present most of my stuff within Cameo, and it's successful. Leadership has gotten used to the diagrams and all that. And then constraint-driven architecture will be more heavily utilized, so more alternatives can be created and tested automatically instead of manually. So right now, it's a little bit laborious to create all of these different alternatives. If you're doing like a feasibility study, you've got like 3 or 4 different options. It takes some time to set up, but as we move forward, we'll be able to use more and more data, and instead of just comparing 2 or 3 things, we'll be able to compare like hundreds of different alternatives, and we can see that that's already coming down the road. So tools will be able to handle more data and more in a more elegant way. Yeah, so some of the tools are slow and clunky, like it says there. I'm a huge proponent of use the best tool for the job, and we'll likely just farm out all of our simulation related stuff to tools related for that. So like MATLAB, as opposed to doing it within Cameo itself. And that kind of is the same sort of concept with all the other tools. It just requires, you have to be smart when you're architecting, like what tool is going to be doing what function. So it's not just like the architecture of the system of interest, but it's also the architecture of the model itself. So the tools will develop to have an automatic data porting methods and be more robust configuration management techniques. We have seen that the configuration management techniques have significantly improved, but the automatic data porting methods are not as automatic as we would hope. So we'll sort that out as well. So future state is more data handling techniques, more data automation, and greater adoption. I think those are the main points that just want to drive home. And then we'll just be shifting more towards like AI and more data. So the future transformation, more automation, systems engineering jobs will become more focused on creating clever constraints more than setting up and doing all these manual efforts to make sure everything's on the same version and building reports and entering data. That will become more automated, and it's just a matter of setting everything up. And then we'll increase the tunable parameters to optimize system based on emission. So what I meant earlier when I said like we would maybe compare like 3 or 4 different alternatives. So if we're trying to compare like 3 different IMUs to one another to work in a system, so our IMU is our subsystem. One of the tunable parameters is something like update rate. So you'd have like you could tune your IMU to update every at 2 hertz or at 5 hertz or at 10 hertz. It will have different ways to do it, and that each way will have its pro and con. I mean, if it's updating really fast, then it's outputting a lot more data, which might be a problem for like memory and stuff. So basically, if you've got more than just one tunable parameter, but like a list of like 10 or 12, your future state would be optimizing all 10 or 12 of those tunable parameters within each IMU. So now you would say, okay, I've got one IMU configuration with 10 different tunable parameters that can be all tuned 6 different ways, and you can see all the permutations that you would get just from having those like 10 tunable parameters. So then you could compare IMU 1 to IMU 2 to IMU 3, but the best version of IMU 1, IMU 2, and IMU 3. Hope that was able to be understood there. So this is my last slide, and then I'll pass it over to Jeff. So here's my analogy. It's Susie writes an essay. So in 1983, I just made them 20 years apart. So and so in 83, she was going to the library, and she reads her book, she finds a passage to quote, she frames her essay, she writes her essay, and then Google comes out, and you know, Susie is writing an essay again. So instead of having to read the book, she Googles what she wants, and then Google will give her passages, and now she doesn't have to read the whole book. She just reads the passages and then frames the essay and then writes the essay. And then now, you know, with Chat GPT and the AI sort of stuff, now you don't even really have to read anything. You just have to frame your essay, question and answer really well, and then the Chat GPT would give you an essay, and then you would have to edit that essay to make sure it's correct. And so there's a lot more work on these edits, and then there's a lot more work on the framing of the question, but it's probably easier than reading the entire book, or, you know, option 2. So that's kind of paralleling what's going on here, except for the digital engineering is like 20 years behind. So we're at the paper-based engineering, where the disciplines send each other paper documents and just kind of threw it over the fence, if you will. And then the consuming engineers had to sift through all the documentation to find the call out that they needed. And so then they would often get a go or no go answer. Yes, I can fit this software CCA inside of this block, or no, I got to have more space. So then there's less time for optimization with the paper-based approach. So now that we're where we are now, we're all using like CAD tools, simulation tools, and such like that, but we're still kind of just we're not really integrating the tools together as but we're getting there. So the tagging and the keywords allow for a faster way for the other disciplined engineer to find the call out that they're looking for, essentially. So I'm trying to say, like, this is the book, and then this is the quote. So now you don't have to look through all the documentation. It's much more accessible to you. So you get to spend more time on creating objective functions, which are manually created, but you get to spend more time on optimizing your system. And then you can figure out what is the best configuration and move on. So the next path forward would be your engineer frames how to constrain the design. Just like your essay, you would frame, you know, the constraints of your essay, what the context would be and how you want it answered. You do the same thing with your system. You'd say where your design space is, where your trade space is, and then the AI would be able to tell you the optimal solution. And then you would have to, just like this one up here, Susie edits the essay. We would definitely have to spend a lot of time making sure that the AI is not cheating physics. So with that, I'll turn it over to Jeff and he'll finish us out.
All right, thank you, Will. So what Will did is he took you to the next depth level of understanding the model-based system engineering, and all the details of what you can do there and how it can help us in a given project. This is Jeff's view. And I think with many projects doing that, this will eventually lead to what I consider, and this is really my almost one slide. I put 3 slides in at the end here. This is really the one that I want to talk to most, because where that fits from a DoD perspective, and I work for the air part of the U.S. Navy as an engineer, and we're dealing with much more complex systems than we did, you know, even 5 or 10 years ago, let alone going back 20 and 40 years ago when I started as an engineer. I was working on a system with 56K of memory that didn't have to talk to anything else, except it did have to transfer some data. But my gosh, what a different world we're in. From a DoD perspective, they actually took in 2018 this new thing coming along, developed from the unified modeling language to SysML to how that was going to work in the future. And the outer layer, it was developed as this 5 set of major goals that we needed to achieve and make digital engineering happen. Digital engineering is not a replacement for systems engineering. It's a huge set of tools in the toolbox to do the system engineering work that we've always had to do and always will have to do. And I know last time I presented a short timeline of what that looks like, but we're still doing the same stuff. The point here is the lowest goal, or the 5th goal in this view from a DoD perspective, from the Navy NavAir perspective where I'm at, and then I'm seeing is right now we're working really hard on the government DoD Navy side to transform our culture and our workforce. And a big part of that is learning how to do model-based system engineering in those 3 major pillars of it, which, you know, having a language right now, SysML is kind of the language based on UML, but I don't know of any other up and coming. But there are a number of tool suites like Rhapsody, Cameo, and others. And we have already run into challenges where a major contractor that supplies a new major air platform did a lot of work in Rhapsody, but now on the government side, we said, we're going to do all this in Cameo. Well, guess what? You drop Rhapsody stuff into Cameo, it's in SysML, but it doesn't work the same way. And we're seeing that. So the other part is getting people to think in a different way. It's really a huge cultural shift, because a lot of folks think that, well, we're doing digital engineering now. I've been doing it for 30 years because I've always written my stuff up in a computer. It's in a digital world. it's all soft, it's not in paper. Well, in fact, it really is, because there could be multiple definitions of the same requirements. It led to things like in the first Iraq wars back in the 90s, we had airplanes using a system called Link 16 that couldn't talk to other planes using Link 16, because guess what? Each project was in its own silo, defining its requirements and then designing to those requirements in different ways, because they didn't have this authoritative source of truth. We have one person that controls the box, designs it so they can all talk to each other. Instead, we had different platforms and different ways of implementing the same high-level requirements, but it didn't go through this common path and a common source. So what this circle represents is, yeah, the outside layer, the skin we have to break through, is getting the culture, the people, the engineers understanding and knowing how to use model-based systems engineering in those three pillars: the language, the tool, and the methods. But then in order to truly achieve that future state, those things that I believe Will is presenting to you and that I'm still seeing us struggle with, is the fact that we need to also, to get to goal one, that's the upper left side of formalizing development, integration, and use of models. Well, in order to do that, we have to get the MBSE in place. It's 3 components, but it also means we have to have an environment that can support a lot of data that's all soft and has single sources of truth, as in number 2 there, upper right corner of the inside of the circle. Providing authoritative source of truth capability means that we're going to have to way of establishing a lot of trust that we currently are challenged with. To trust somebody, it's like for years and years how we thought we were going to have a lot of reusable software and we're going to have a lot of trust and we would all reuse that, and that was never really achieved at all effectively, in my opinion. The details of this goes into how are we going to establish an infrastructure that can make that connection happen between a lot of huge system of systems that have to have in different weapon systems and different platforms. Those are airplanes that carry those weapons to be able to do their job and let the pilot come home safe and get rid of the bad guys. I'm just being really blunt about, in a DoD perspective, what we're trying to accomplish. That also means things like we have to incorporate the innovation into technology. Number 3, lower left corner there. That really goes back to when you look at the details in the next slide. It shows the details, but it's really just an eye chart. I can give you references. They're included in here. This view is actually came from a set of measurement frameworks that were developed for digital engineering. And if you're familiar with things like capability maturity models, the way that we've applied those using personal and team processes and all the foundational things that we're doing now to try and innovate our workforce so they can do innovation faster than the enemy, it really comes back to we're going to have a new way of making this happen. And the bigger picture here is MBSE is one of 5 major components of achieving the future of digital engineering. And it's going to take some time with a lot of innovation and really rethinking outside the box. Companies like Raytheon and others, where Will's at, have been doing this kind of work on some specific projects and getting great strides. On the government side, we're still challenged trying to figure it out and penetrate that outside layer of how we're going to transform our own culture. Working that now. Some progress is happening. I was just in a meeting yesterday. We're looking at our own version of a boot camp. I know that actually it's not our version. I know, Will, you teach a boot camp at Raytheon for your folks. What we do in the government is often ineffective training. Now we're looking at Stevens Institute. They're Georgia Tech, or part of Georgia Tech. They're part of this big alliance of defining system engineering. they've developed a slow, fast learning approach to digital engineering that touches on all 5 components here. And we're looking at how we're going to bring that in to start to evolve our culture within the government because of the things that we're dealing with in this change. So what I'm telling you, I guess, overall is digital engineering is a huge thing. 5 major components. Achieving goal 1, that purple stuff, formalizing the development of the use of models, rests on establishing and how are we going to handle authoritative source of truth. That means we don't have link 16 boxes in multiple platforms that don't know how to talk to each other, because they're all based on different ways of analyzing the requirements of the design. We're going to have one source and everybody subscribes to that or uses that, etc. It's going to require the processes that we use today for all the engineering work we do to have these considerations for digital engineering, but they still have to achieve the basic stuff that we've been trying to use for many years of getting people to plan the work, keep the planning alive as they're subscribing to the plan, and make the plan live and breathe as we discover new things about the project that we're working on. And of course, the internet is getting faster. We're going to have to, especially on the government side with secure systems, how are we going to handle new ways of allowing people to share sensitive or even classified information that goes across these huge system of systems? Raytheon, as one of the major suppliers of a lot of the systems, we contract out to have them develop and build those systems. How are we going to share data with all of our major contractors from a government perspective, from a DoD perspective? There's a lot of detail that goes with that. So I've done a lot of talking to this one circle, but I really think it's a great way of looking at this. MBSE is the starting point, but there's a whole lot more to go and deal with. The reference down there, there's this DE measurement framework. It was actually led by our friends in the Army, PSM based, but also working across, IEEE, Stevens Institute, and others to come up with it. It's a great document to refer to and look at those basic measurements and ways that we're going to derive metrics for how well we're doing in achieving this digital engineering, digital engineering way of doing stuff. So if you go to the next slide, so here's the eye chart of that. And I mentioned this was pulled together at the highest levels in the Department of Defense on the left side in 2018, when these 5 major goals or ways of making that happen emerged. There was a formal document that came out, and it contains that. Well, over the next couple of years, that led to the Navy's strategic approach for how we're going to make that happen. And it laid out these same 5 objectives, ones I was talking to in the circle and the way they're arranged on the previous slide. But it's really, the details are here. Like I said, it's an eye chart, but when you look at it, it makes a lot of sense that, yeah, we start at the bottom and transform the culture. We provide lots of training on the 3 major pillars of model-based system engineering, getting people to start understanding that and using it on actual real projects, so it becomes repeatable and sticky. But again, it requires objective 4 that we start to make these connections happen. Objective 3, the details there really lay out how we're going to in some kind of agile, and agile is spelled with a lowercase a. It's all about the agility to make decisions quickly, to have access very quickly to the way things were decided and documented in some way that we can all trust. That's what objective 2 on top of that is really all about. How do we have these authoritative knowledge sources of how a system and all of the components it's made of, so systems of systems, how do they get defined and owned by one authoritative source, so that we all trust that, and then we use that to build the systems that we need from those component parts and pieces. And at the higher levels, we build different weapon systems that go on different airplane platforms and those all to come together in a big wartime environment. So, now you're 3 levels up at least in systems of systems of systems, and you can go on from there. But all of the details there provide how are we going to handle that complex world. And really, it leads to then the highest level, the objective 1 or goal 1, which was formalizing that. It really rests on top of all of these things happen. And then how do we do the implementation, carrying that out? This is going to be many years, just like Will showed in getting MBSE in place and how it's evolved over 20 years, even 40 years. Well, I think we have a lot of work ahead of us. And my point here was really just to come back and say, here's all this MBSE stuff. We got to deal with it and make it work. But my gosh, I think it's just the beginning of the huge world of how we're going to very quickly be able to handle these huge complex systems. And if we don't do it, I think it's going to hinder us. I know from within the government, DoD, Navy perspective, we see that we have got to get a handle on this. And companies like Raytheon and others, they've already started down that path. They're ahead of us, and we have got to do some catching up. So I'm just being really scary and blunt and honest that the bigger picture is what's needed. Now, on the last slide that I have, the next slide, this is really just from that same digital engineering measurement framework. There's some detail in there that to me is very interesting. There's kind of 3 core concepts at the digital engineering level to go across those 5 objectives or goals. And they're all tied together here. And the things I've highlighted in red are kind of pointing out the fact that every artifact, every black box, every component that we put together to build a weapon or a platform system, how they interact, every one of those is going to be eventually owned by what needs to become a single entity where they manage it, they control changes to it, and everybody else subscribes to that. Those model elements then need to, these 3 bullets under number 2, it's an abstraction. It comes from what was represented as a need to perform in a certain way. Each of those is going to be, those model elements in that ASOT that we talked about on the first level, the authoritative source of truth, that needs to come from some really advanced development processes. And by advanced, I mean well understood, that we're doing practical things, that we're carrying out, the use of data, we're collecting useful data and we're using it and actually applying it. That's really then what goes into the life cycle phase number 3. And, the 3 major bullets there talk about the evolution of this system, the phase and what it represents. But really, I think that the 3rd bullet was the key thing that grabbed my attention and ties it together across these highlighted parts, that in a digital engineering based project and then a system of projects that all have to produce things that have to come together. Again, it ties back to all of those artifacts have to be managed, decisions have to be made from an authoritative source of truth perspective. That's what's going to make digital engineering happen. That's what's going to take advantage of using MBSE to document things in a way that everybody can look at it, understand it, see how it performs, and then based on that, they can take the components, the building blocks, and put together these more complex systems from all those component parts. So that was the details of what's behind what I consider that circle of what are the 5 major pieces of digital engineering. MBSE is the outside layer. We've got to get through that, get people using it, understanding it, and thinking that way. But then the other 4 components kick in to make the true DE experience happen and work for us and make very complex things doable and in a way we can deal with them.